Good morning, students. So, in this session from chapter number 2, MOSFET and its DC analysis, myself Madhuri Mulik, working as assistant professor in Electronics and Telecommunication Department, Sharad Institute of Technology, College of Engineering. So, last time we have discussed the circuits which are used in a MOSFET. So, now we are going to proceed that same thing in continuation. So last time we have covered MOSFET as diode, then current sink and source, current mirror, voltage references and band gap references. So now today we are going to see CMOS inverter as an amplifier. So that are active load, current source and push-pull configurations. Okay, so let us start with the CMOS inverter as amplifier because these points already we have covered in the last sessions. So already we have seen the MOSFET as a diode and active resistor, current sink and source, then current mirror we have seen, then voltage references we have seen, then band gap references we have seen. So now we are going to see CMOS inverter as amplifier in that active load, current source and push-pull configurations. So CMOS inverting amplifiers. So the CMOS inverting amplifiers, that is complementary metal oxide semiconductor. So here some characterization of amplifiers are listed. So large signal voltage transfer characteristics, large signal voltage swing limitations, small signal frequency independent performance like gain, input resistance, output resistance, then small signal frequency responses, then other properties also we are going to see, that is power dissipation and etc. Okay, so these are the characterization of the amplifiers. So let us see the inverters. The inverting amplifier is an amplifier which amplifies and inverters, the inverting amplifier is an amplifier which amplifies and inverts the input signal. The inverting amplifier generally has the source on AC ground or the common source configuration. Okay. So inverters means what? The inverting amplifier is an amplifier which amplifies and inverts the input signal. So the inverting amplifier generally has the source on AC ground or the common source configuration. So various types of inverting CMOS amplifiers. So we will consider here that active PMOS load inverter, then current source load inverter and push-pull inverter. So see here the active NMOS load inverter, okay, then active PMOS load inverter, then depletion NMOS load inverter, then current source load inverter and push-pull inverter. So the circuit arrangement for the each inverter is shown here. So active load inverter. So here the active load inverter circuit diagram, circuit arrangement is shown. So 5 volt supply is given for M1 and M2. So N type and P type PMOS are used. Here we are applying the V in for the M1, and the source and gate is shorted for the second transistor. So while if you see the W2 and L2, these are the 1 micrometer, but for the M1, the width and length, that is 2 micrometer, that the width, and 1 micrometer is the length. So see the voltage transfer characteristics of active load inverter. So for the active load inverter, so this graph is nothing but the ID versus V out. Okay, so various values of various values of that the input, we have taken V out for the active load inverter. So according to that, we have plotted V out versus the V in. Okay, V out versus the V in. So these same points, that is A, B, C, D, E, okay, from this graph to this graph. So see here, dotted line shows that alternate action of the M1 and M2. Means what? For this line, okay, M1 is in the saturated region, while M2 is in a cutoff. Then for the next line, M2 is in the saturation region and M1 is in a active region. So the boundary between active and saturation operation for M1 is, that is VDS1 is very greater than the VGS1 minus VND, or we can say V out is very greater than V in minus 0.74. Okay, so this graph represents that voltage transfer characteristics of the active load. So for this circuit, we have taken ID versus V out. Okay, ID versus V out for various values of V, and we have transferred that into V out versus V in. So we will get the same point as the first graph to the second graph. So large signal voltage swing limits of the active load inverter, that is maximum output voltage V out. So V out max is equal to VDD minus in mod of VTP. So ignores subthreshold current influence on the MOSFET. So minimum output voltage V out means, assume that M1 is non-saturated and that VT1 is equal to mod of VT2 is equal to VT. So VDS1 is very greater than VGS1, comma VTN. That same equation is written like this. V out is very greater than V in minus 0.74. So the current through M1 is given by ID is equal to beta into VGS1 minus VT into VDS minus VDS1 square divided by 2. So we are going to put the value of VGS1, that is VDD, and here VDS1, so V out minus V out bracket square by 2. And the current through M2 is given by ID is equal to beta 2 into 2 VGS2 minus VT bracket square is equal to, so modified after the putting the values of VGS2, that is VDD minus V out minus VT bracket square is equal to beta 2 by 2 into square bracket V out plus VT minus VDD. So equating these currents gives the minimum Vout is as, so Vout mean is equal to VDD minus VT minus VDD minus VT divided by root of 1 plus beta 2 divided by B1. Okay. So large signal voltage swing limits of the active load inverter, that is comes here. Then small signal midband performance of active load inverter. So the development of small signal model for the active load inverter is shown below. So this is nothing but the active load inverter, which is converted into small signal model. Okay. So from this input side and output side, the sum the currents at the output node is get GM1 V in, GDS1 V out, GM2 V out plus DS2 V out is equal to 0. So solving for the change gain, that is V out divided by V in, gives, so it gives V out by V in, that is voltage gain is given by minus of transconductance of the first MOSFET divided by GDSL plus GDS2 and G only G into M square. So 1 upon 8 M square. Then let us see the performance of an active resistor load inverter. So here one example we are going to see. So calculate the output voltage swing limits for VDD is equal to 5 volts. The small signal gain, the output resistance, and the minus 3 dB frequency of active load inverter if width by length ratio is 2 micrometer per length and W2 divided by L2. So it is 1 micrometer divided by 1 micrometer. So GDL 100 picofarad, 200 picofarad, 100 picofarad, 200 picofarad. Cp is equal to PL and ID1 is equal to ID2 is equal to 100 micrometer using the parameters in the table. So from the above result we can find V out mean small signal voltage gain including is GS1 and GS2. Then lambda we have calculated and P, that is minus 64 into 1 into 10 raised to 6 radian per second. So thus 3 dB frequency is 10.2 megahertz. Then current source load inverter we are going to see. So in the last, that active inverter, that gate and source terminal of the M2 is connected to each other. But what is the difference between these circuitry? Here no any gate and source is short circuited. Instead of the gate of M2 is connected to the some reference voltage, that is 2.5 volt, and rest of things as it is same as that the CMOS inverter for active load. So for the current source inverter, voltage transfer characteristics is given by, so ID versus V out, same thing is applied here. So at the different values of VE, the graph is taken and plotted. So from this graph, we know this point as well as we know the VE. So it is going to calculate. So VE is 255, VE is 2 not N, sorry V, and 1.5 and 1.0. So large signal voltage sweep limits of the current source load inverter. So maximum output voltage V out is defined by V out max is equal to VDD. So minimum output voltage V out mean is given by this formula. Assume that M1 is non-saturated, the minimum output should be. So V out mean is equal to, in bracket, V out mean is equal to VDD minus VTT under square root of 1 minus beta by B1 VDD minus VG minus VT to VDD minus VT1. So the small signal modified performance of the current source load inverter is given by, this is small signal models. So which are the small signal models? Current source current, then this one. Then midband performance is plotted here. So log rhythmic amplitude versus the ID. So for this, it is the, from the starting point of view, it is somewhere 0, and after that it is going to reduce. So this is say as a strong person, this is say as a right person. So let us see performance of current sink inverter. So here the current sink inverter is rearranged. So here the reference that we have removed and keep okay. So the performance of a circuit sink CMOS inverter, it is examined. The current sink inverter shown in a figure show assume that these are the length specification, width L1, width L2. VDD is equal to 5 volt and VGGR is equal to 3 volts. And the temperature of table 3.12 describe M1 and M2. Use the capacitor values of example. CDL is equal to CGL2. So calculate output swing limits and the small signal models. Have you seen this circuit diagram? Then let us see the solution. To attain the output signal swing limitations as a current source CMOS inverter with PMOS parameters for the figure, current sink CMOS inverter as the current source CMOS inverter, using a prime notation to designate the results of the current source inverter which exchange the PMOS and NMOS model parameters, we get V out is equal to, so V out max is equal to 5 Then V out is equal to minimum value of this, which is uh, multiplication of the point, not point 0.5 to 5 to 0.7. So the value comes like this. So in terms of current sink CMOS inverter, these limits are subtracted from 5-volt gate. So V out gate 4.27 and V out is equal, mean is equal to 0. So to find the small signal performance, we must first calculate DC current. So the DC current ID is given by this equation. So if you want, you have to put this which available parameters are there, and you can prepare. So in this session we have seen that the MOSFET MOSFET's characteristics. Thank you.